speakers. There will be Ramesh somewhere. He's already here. He will join later. And for the first talk, we have Stefanie from Passau, and she is telling us a little bit about nails and hammers, I believe. So please go ahead.
Thank you for having me here. I'm a repeat participant of SummerSOC, but I'm a first-time speaker. So I'll be talking about this idea of using quantum devices as co-processors in data management or for databases. So that's going to be our hammer, and now we're looking for suitable nails in data management. It's going to be partly an overview talk of what people have been doing, and partly also a bit of an overview of what my group has been doing here. So I need to work two devices here. Okay, let's start with some expectation management about this technology. I know quantum computing has always been a big part of SummerSOC, but just to make sure everybody's on board where we are. Here's a screenshot of IBM Compute Platform, and they offer you various quantum hardware devices for rent commercially via the cloud. And this overview table, I think, is really, really revealing as to the state of the art of the technology. First of all, the first column is really qubits. So here we have 156 qubits. That limits the size of the problem you can offload to the quantum computer. Now just imagine if you wanted to solve a problem and I only gave you 156 classical qubits to encode it with, or classical bits to encode it with. That would be tricky, right? So we are currently limited to small problem sizes, and I have this icon of the chest of toys here, and that's going to pop up again and again in this talk. Then there's a column on error rate. So those systems are very error prone, they're very noisy, they are high maintenance, so luckily here they're all online, but they may not be. And you have quite considerable latencies to deal with. It's a cloud service, so you lose time accessing the system over the cloud. And here there's a queue of over 1,000 jobs ahead of you. So if you're trying to get something done on IBM Pittsburgh at the time of the screenshot, you would have to wait for 1,000 jobs before you to compute your turn. In addition, it's quite an expensive technology skill. So that's the current billing plans, and the cheapest plan, if you buy in bulk, is about $50 per minute. Now, if you spend $50 per minute on computing, there's a lot you can do with classical hardware on that, right? Having said all of that, you may wonder, well, why are we interested in investigating this technology as co-processors? And I'm from data management, so the question is, what's in it for data management? Well, the hardware may be still immature, but I think it's mature enough to do research. So it's time to get started. And also building up the required skills takes time. How to use a quantum computer, that's not part of your standard bachelor's computer science program, so people need to learn. Also, I think the prognosis is very promising. The hardware will get better. It will get more reliable, it'll become cheaper, and the software tooling infrastructure will get better too, so it can only get better from here. I think it's time to now get started so that we're ready when the technology is there. In particular, the domination of my research group is actually database management systems. So what's in it for database management systems? Database systems solve computationally expensive problems that are commercially very relevant. So I think we have a super interesting use case for quantum computing because there's a market behind those problems. From my point of view, it's also important to engage in this opportunity for hardware-software co-design. If we now participate in working with the technology, we can shape the technology. So we can make sure that the software interfaces and the libraries and the benchmarks and everything that is being built today by the compilers group and the software engineering groups, that it's going to be in a way that it's useful for us. And that's actually been my experience in collaborating with people who build programming languages for quantum computing. That they're really grateful for the feedback. So what are current research questions that are being asked in my field? The first question, and that's going to drive this talk too, is which problems are even suitable for offloading? Yeah? Then how can we correctly encode those problems for offloading? How do we get them there? At the moment, we're not expecting speed-ups or anything at this point, but we can ask Are the solutions that we obtain, are they qualitatively different? Do we get different solutions? And then there's the big question how we even integrate this kind of hardware into a database management system. Okay. Before we can actually look for nails, or we can hammer on with this technology, let me give you a big high-level background on this technology, and I'm going to start talking about QUBO. Now that's a formulation for optimization problems. It stands for quadratic unconstrained binary optimization problems, and you may already know it from simulated annealing or similar techniques. Now you may ask, why QUBO? Weren't we supposed to be talking about quantum? Well, QUBO is really what my community has been latching on. So here's an overview from an ICD 2024 tutorial. It's a really nice overview. What are the problems that people have worked at? Query optimization, data integration, transaction management. And how did they formulate the problem? QUBO. Not everybody, but pretty much everybody is going down this path. So I want to give you a high-level introduction what's happening on this path. Okay. The idea in formulating a QUBO model is to describe an optimization problem as an energy landscape. And the goal will be to find minima or maxima in this energy landscape. And you may be familiar with that already from simulated annealing. So you formulate with QUBO a quadratic polynomial with binary variables. They can only have the values 0 and 1. And let's say we want to find maxima. So in simulated annealing, which is a very established and mature technique to solve QUBO models on classical hardware, you do some hill climbing, you may do some perform a jump to some other hill, hopefully a bigger hill, and then you do some hill climbing again, and then you jump, and that's how you traverse this energy landscape. In quantum annealing, it's the same goal, but you have different ways to navigate this landscape. For instance, there's a technique called quantum tunneling, which allows you to just drill through one of those hills and see what's on the other side. So those QUBO models can be solved by quantum annealers, which is one family of quantum hardware, but also gate-based QPUs, that's another family of quantum hardware. The annealers are designed for optimization problems. The gate-based QPUs can do much more, but they can also solve those optimization problems with an algorithm called QUAVA, which mimics this annealing process. So we're being really, really high level here, just getting you the idea. Okay, so what many people have been doing is formulating QUBO models. Now, how would a piece of quantum software look like if you're trying to solve a QUBO model? You have some optimization problem, and in pre-processing on a classical hardware, you turn that into a QUBO model. You offload the QUBO model to the quantum annealer, and you have various tuning knobs, and one particular knob is the annealing time. How much time does the device get to solve this problem, find a minimum or maximum? That's going to output one bit vector. This bit vector is the assignment of the binary variables in this QUBO model. And those bits are ultimately going to be mapped to the qubits on the hardware device. Now, if the qubits are our limiting resource, so that restricts the size of this bit vector, and it also restricts painfully these days how many variables you can have in your QUBO model. So that's going to be a bottleneck. This is a probabilistic process. You may be lucky and you find your maximum or minimum, or you may be unlucky and you're somewhere else on this energy landscape. Which is why you don't just compute this once, but there is a loop. So maybe you have 1,000 repetitions, or called reads or runs. Now in those 1,000 repetitions, you get 1,000 bit vectors, but some of those you'll find more often. So really what you're evaluating in the end here is a histogram over frequent bit vectors. And now you need to do post-processing. You have to throw out the garbage, so to say, remove, discard all the proposed solutions that are not working for you, and hopefully you find one good solution. That's our workflow on a quantum annealer. If we had a gate-based QPU, it would be similar, just that in between here, there would be another loop mimicking this navigation on the landscape. Now, if this is our hammer, what makes a good nail? And good nails are here optimization problems. They are small to encode, so they cannot put much data on the quantum computer, and because those qubits are scarce. The problem should have a high classical complexity, But then the pre-processing, the post-processing, those should be cheap. Now that's not where you want to do the heavy-duty lifting. That's where you want to do the heavy-duty lifting. With this perspective, let's look at some nails that people have so far hammered up at in databases and data management. Okay, quantum computing for database systems. What's the most important task of a database system? Query optimization, right? And I'm going to start with the first paper in this domain, which was on multi-query optimization. That's a paper by Emmanuel Trummer and Christoph Koch, where they offloaded the multi-query optimization problem onto a quantum annealer. And I really say this is a pioneer work, because they did that 10 years ago. And 10 years ago, you didn't have quantum devices as commercial services in the cloud. You had to know somebody who had an annealer in their lab and who would give you access. And you didn't have nice programming frameworks like Qiskit and PennyLane. It was a whole different story. So that's really, I think that's a pioneer paper. And they started out the Cubo way. They were the first to come up with this idea, and pretty much everybody has been doing Cubo since. There's been various follow-up works also putting this on the gate-based quantum computer and so on. I want to give you an overview of how they went about to solve this problem. It's a very practical problem, but what we'll notice in a second is the level of abstraction where they're targeting the problem is extremely high. And the simplifying assumptions that they apply, they're plentiful. Yeah? But I'm not saying that to put down their work. I think it's really fantastic. It is a pioneer paper. So in query optimization, let's say you're a query engine and you get 3 queries to optimize. And then for every query, you have some alternative plans, and all those plans come with costs. And if you optimize them individually, you're going to pick the cheapest plan per query. If you're going to optimize them together, you may consider that combining certain plans gives you savings. So those could be sub-expressions in the query plan that you can reuse for 2 queries. Now the multi-query optimization problem here is the challenge of picking one plan per query, keeping the overall cost as low as possible, considering the individual cost for each plan and the savings that you get by combining the right plans. And it's really on that level of abstraction where they encode the problem. I'm going to show you a peek at their Cubo model. I'm not going to walk you through it in detail, just highlighting some things. So we said it's a polynomial over binary variables. So our binary variables, there's going to be one binary variable per plan. And if it's 1, the plan is going to be selected, and if it's 0, it's not. So the number of qubits ultimately limits the number of plans we can even consider. And then they craft a polynomial where each term shapes the energy landscape in a certain direction. We want to minimize the energy costs in this energy landscape. And there's one term that ensures that you select a subset of all the plans. There's one term that says we only want at most 1 plan per query. Query doesn't need 2 different plans. We have to reduce the total execution costs, considering that we get a reward for sharing. I'm not going to walk you through the details, but it's still, the formula is still simple enough that you can think through it piece by piece. That's a thought I want to hold, because I'll get back to that in a second. Okay, so that was their pioneer paper, and again, on a very high level of abstraction. What's even more essential than multi-query optimization? Join order optimization. If you get that right, your database is going to be successful. Join order optimization is this problem of finding the right join order, and you have those binary trees where the leaves are relations, and you have to find the right shape for this tree, and the search space is very big. It's an NP-hard problem. In collaboration with Manuel Schönberg and Wolfgang Maurer from OTH Regensburg, we wrote the first paper on join order optimization. And I dare say it's also a bit of a pioneer work. That's 3 years ago that it was published, and we've had several follow-up works since. I also know that here at the University of Crete and at Forth, they're also working on join order optimization. All of that following up on our approach. Our approach started out with a known optimization, or the known formalization of the join order problem as a mixed integer linear programming model. So a different optimization model, and then with an interim representation, we reduced that to a cuboid model which we then could optimize, and we could only handle left deep trees. So there were two downsides to this first approach, right? We had those intermediate representations, and every time you're rewriting the problem, you're losing something, and then we could only handle left deep trees. That's been overcome now in follow-up work. They go immediately to Kubu, and they can also manage bushy trees. In fact, there's one demo by Ibrahim Sabek's team where they have SQL queries where when they compare the performance of the Postgres optimized query and the quantum optimized query is faster. So we get, in some cases, better query plans. That's the first careful attempt of actually showing this for realistic queries. So that's a line of work that's still very active. I want to highlight for you one little excerpt of our experiment where we ran the join order optimization on a D-wave quantum annealer with 1,000 annealing runs, and we're ramping up the annealing time in microseconds. So those are all parameters we met in our workflow before. And I'm waiting for Bernhard to cry out. We can optimize the join order for 4 relations, and it breaks down for 5 relations. Now the hardware is 3 years old, but still, come on, right? Among 1,000 attempts to solve this problem, not a single bit vector that was returned for the 5 relations gave us an optimal solution. Some still gave us even a join order plan that makes sense, but it's not optimal. So we're stuck with toy problems. If you look at a series paper that does join order optimization on classical hardware, they are joining 40, 50, 60 relations, so an order of magnitude bigger. It's just toy problems. At the same time, we've shown it can be done. We found a formulation that works, and for toy problems, it gives us an output, but we're limited by the state of the hardware here. So join order optimization is a big, important problem. I also want to talk about data integration, especially since I know there's many people working on data integration here. And an important problem in data integration is schema matching. So that's the challenge of merging data from 2 tables. So you have one table with person data, first name, last name, and here it's a composite name. There it's a composite address, that's a street number in the city. As a human, just looking at it, you have a pretty good idea how you would match those columns when you were to merge the data into a common table. The schema matching problem is very well researched, still an active area of research too, and it's usually attacked in 2 phases. In the first phase, you take all the attributes from the one table and all the attributes from the other table, and pairwise you compute some kind of similarity score. That could be based on the name of the column, or the content of the column, or the position in the column in the table. There's countless approaches. Once you have that, you have to decide whether the last name should be matched to the name or rather to the street number. So you have to find a global matching, and at its heart, this can be reduced to the stable marriage problem. So think of eligible bachelors on this one side who have a crush on eligible bachelors on the other side, and they have their preferences, whom they would like to marry. You have to marry everybody off, and they have to be, in the end, they should not be so unhappy that they get divorced. That's the stable marriage problem. It's a mathematical problem that you can formulate. And this is what you need to do in global matching, and there's variations that are NP complete. So in a master thesis with a really gifted student of mine, we thought, well, why not tackle the global schema matching problem with quantum computing? We take the schema matching problem, we build the demo end-to-end, where we are doing this local matching, and then the global matching, we reduce that to the stable marriage problem, and we used an existing published QUBO model for this stable marriage problem, and then we did this end-to-end, and for toy examples, we could actually demo that. So that was a published demo. And this QUBO model here, my student annotated it in her master thesis. She went through great pains trying to understand what it really does. Now this is a really nice paper by Claudia Linhoff-Popin and Sebastian Feld from LMU Munich, and they introduced this QUBO model for the stable marriage problem. But when we tried to re-implement it, and then later on we got their code did different things from our code. So we didn't know, was it a bug on our side, was it a bug on their side, maybe we didn't understand the model. And I found this really frustrating because this model is now big and bulky and complex to think through. And that irked me, this problem that you have some QUBO model that you have to believe at faith. So in a second attempt to tackle this problem, I teamed up with Nicole Schweikert. She's from database theory, and her master student Luisa Gerlach, and we were joined by Tobias Köppel and René Zander. They are from Fraunhofer Focus, where they're building a programming language for a programming framework for quantum computing. And we revisited this global matching problem. We made it a bit more general, not just one column matching to one column, but we kind of 1 to n, n to 1 matchings. And what we now did different, we formulated this problem as a polynomial. It's no longer a QUBO polynomial because the polynomial degree is higher, so we have to solve it on a gate-based quantum computer. But we formally show that this polynomial is actually a formulation of this schema global matching problem, that if you solve this, you get a solution to the original problem. So we we have a correctness proof for this polynomial, and we show that this is actually NP complete to solve, because my suspicion is that some QUBO models out there, they may not even be that expensive that you would need quantum computing. And we have a proof of concept implementation where we show that for small toy examples again, but these are examples from real schema matching benchmarks, we can actually find solutions to this problem. Okay. So that was a whirlwind tour through existing work on trying to couple or integrate quantum computing hardware into data management and databases. We've looked at query optimization, multi-query optimization, and joint ordering. We also looked at schema matching. We have not looked at transaction management. That's work done by Sven Groppe, who was until recently at University of Lübeck. And this tutorial, that's not a long time ago that was published, but there have been a lot of other attempts. So people have worked on index selection, which indexes to pick in the database to accelerate it. People are working on data allocation, and I'm mentioning this because there's researchers in the room who do distributed systems. So the question, on which node should my data go, that I can evaluate my queries efficiently. There's work on entity matching, which is also data integration, but different from schema matching. Here at the University of Crete and at Forth, there's schema discovery work going on, and also work on actually encoding and indexing knowledge graphs using quantum computers. To the best of my knowledge, they are pretty much, they are one of the few ones who don't go down the QUBO route, but they try out different things. Me and my team were actually working on query containment at the moment. So far we have a technical report. That's the question. If you have two SQL queries, well, for SQL in general it's undecidable, but if you have two conjunctive queries under set semantics, is one query contained in the other? And you can use that to check for query equivalence, and that's great because if you have a query with a very expensive plan and a query with a very cheap plan, and you can prove that they're doing the same thing, we're just going to pick the cheap one. And what I find particularly exciting here, this is a problem that's not implemented in database systems today because it's just too expensive. Whereas with join ordering, you're competing against decades of engineering and research with your little quantum device and join ordering there. Okay, that's already my last slide. To sum this up, there is a quest for suitable database systems for good nails, and that quest continues. So far, it's mostly QUBO formulations. So far, most of those QUBO formulations are presented on faith. They're explained to you, and you have to believe them. And that's something that ticks me, and that's where I'm trying to enter the field and think we can do better than that. So far, most experiments are in vitro, outside of a database management system, with generous simplifying assumptions and just toy examples. But there's also first attempts ongoing at integrating this technology in database systems and to figure out where to integrate them, how to connect them, how to build a robust software stack. With that, I thank you for your attention, and I'm eager to hear about your questions.
Yeah, we are open to questions. Yeah.
Okay, thanks, Stephanie. I really like the way how you actually put it is in a very academic debate format, because I think we typically joke about, if you're holding a hammer, the job it becomes actually, now you're actually just focusing on the nails. But then normally this is what we typically tell our students, we should not do that, right? So
Exactly.
I think in that sense, I will take this more critically, asking you this question. So now you actually put a lot of problems that you try to actually fit into the tunnel of using quantum. So what's the difference between using another different kind of technology that's powerful enough, a large language model, and then try different kind of mechanism to actually solve the similar problems, basically the same nails. What is actually the fundamental reason? Why are you so focusing on the quantum? Maybe there is a project or funding, whatever, but maybe there is something actually more fundamental behind it. Can you actually share that with us?
Yeah. So I'm fully with you that we're trying not to. We're telling our students not to do that, yeah, just to blindly find nails. But to be honest, I think that's what my community is doing whenever there's something new. So when there's because we have some really timeless and tough problems, like the join order problem. So when GPUs come out, we try out GPUs. When there's deep neural networks, when they came out, we try those out. When LLMs are there, we're now, people look at LLMs for join reordering or for query optimization. So that is very much in the spirit of my field, that we have those timeless, really tricky problems. We have working systems, but we always think we could do better whenever a new technology comes out. Why quantum? I find this really intriguing because it's such a different way of tackling the problem. Like if you're thinking about how would I model that how would I formulate that as a QUBO model? I think that is an intellectual challenge. And there's actually a parallel line of research where they're taking those QUBO models that people came up with for quantum computing, and now they're going back to simulated annealing and trying to integrate simulated annealing into databases, because those QUBO model formulations that were actually crafted for quantum computing work really, really well on classical annealers also. So maybe even if down the road, not many, I think that's the backup plan also. And there's a lot of intellectual payout, I would say. Let me formulate it that way, in trying to think of how to formulate those problems differently.
Hi, Stephanie. Thank you very much. Very nice talk. As you know, I am more interested in the part of the integration with the DBMS. Do you know of any of those attempts? If there's somewhere out there trying to do that other than what we are trying to do?
Yes. So a lot is happening here, but I know that Ibrahim Sabek's group is really pushing for that, and they're looking. My impression is they're trying to look at D-Wave a lot to integrate that. And then Haris Kondilakis here at the Force, he also goes very much in that direction and seeing how they would fit into the software stack. So I think those are at least to the best of my knowledge, the most advanced efforts in that regard. But this is all still very, very early work.
Okay, last question.
Very short. Thank you for the great talk. Very interesting. I am more on the data cleaning community. So things that one thing that I'm not understanding, the traditional, typical state-of-the-art data cleaning methods do things iteratively, such as the semantic matching. They try one pair, then another, then probably correct in case of errors. So things are made progressively. Now, how does it compare with the quantum-based framework? That would be very interesting to understand to me.
So at least with those QUBO models, which is what the mainstream has been exploring, you wouldn't do that so much iteratively, but you describe your energy function. But there's algorithms like this Krava algorithm where you could tweak the energy function between runs. One could explore that, but I don't think people have really explored it yet. One challenge here, because you mentioned entity matching, is you have so few qubits, so you're not going to get the data on the quantum computer. Right? With the schema matching, we're getting this bipartite graph that I showed you. We get that on the quantum computer, but not the data itself. So all the work around has been focusing on what can we get there, and so far it's not the data.
Okay. Okay, thank you again. She will be here, so you can talk to her later. And now the last talk of this session is by